Hello, hi everyone. Can you see and hear me? If someone can please type in the chat room, like in the chat on the side, just to make sure that that I'm coming. That people can hear. Okay. Thanks, Shiri. So hello, good evening, everyone. Can anyone? Okay, good. Thanks, Chloe. Okay, good. So welcome back to another Stark at Home, accompanying us all while Corona is still doing whatever it's doing. This time, the topic for this time, this informal webinar, is going to be zero knowledge. And as I promised, in various online things, I'm going to try and do it without mentioning the cave example and without talking about where is Waldo, but rather trying to go at it from a different angle. So for those who are new here, or it's been a while and they've attended too many online events, I'll just remind you that I'll be speaking about some stuff, going back from time to time to check, because when I'll be speaking, I'll be using the whiteboard that I'll soon move to, and it will occupy most of the screen, and then I won't be able to see or hear anyone. But when I come back, I'll go and look at the questions. So ask a question, please fill that up, and then we can address the question. You can also type in the chat, but that's a bit harder for me to track and follow, especially while I'm using the whiteboard. So from time to time, we'll go back, answer some questions, and then jump back here. Okay, good. So I will now move to the doodling mode, scribbling mode. And maybe let me just pick some other color pen and change the size so it's slightly larger. Okay, so the topic for today is about knowledge and zero knowledge. What do we mean by it, and then how do we achieve it? So I want to talk a little bit about, first of all, to start with information, because information and knowledge are pretty similar, and I want to talk about information first. And then I want to talk about what do we mean by knowledge and zero knowledge, so moving from information to knowledge. And then I want to talk about the very specific context of ZK, so zero knowledge is abbreviated ZK. I want to talk a little bit about ZK in Starks, and in particular to sort of explain how one gets a ZK Stark, and for that, a lot of it will also be discussing how we get ZK in an IOP. An IOP is an interactive oracle proof, and I'll define or refresh these concepts as we go along. So let's start with information. So information, I just want to move the screen a little bit and start talking about. So information, sorry. So information is, of course, a very loaded word, but it also has a very strict definition in the context of math and computer science. And this goes back to the amazing work of Claude Shannon from the 1940s. And this concept of information has completely revolutionized statistics, computer science, coding theory, electrical engineering, and also has a lot of connections to other areas such as physics and philosophy and linguistics and other things. So informally, what do we mean by information, and how do we quantify it? Suppose there's, I live on some island near the equator, and on a given day when I wake up in the morning, it could be either sunny outside or it could be whatever, rainy. And that's roughly, those are the two kinds of days that could happen, that could occur on that particular island. So when I wake up in the morning, I don't know yet which of the two events is going to happen. So maybe, I know that with 50%, it's going to be a sunny day. With 50%, it's going to be a rainy day. So that's my starting point when I wake up in the morning. Then I, take a peek outside the window and I see a certain view. And what I see is on some day, I see there are some clouds, just a little bit of clouds. So based on this, now I recalculate and I think that, the probability that it will be a sunny day maybe has gone down to, 20%, and the probability that it will be a rainy day has gone up to 80%. And what happened was that I saw or learned or heard of a piece of information, and based on that, something about my view or my knowledge of what's going to happen in some other domain has changed. Okay, so the way you could think of this is that we have this we have a variable that we don't know, some randomness. So in this case, it is the weather. In this case, X is the weather, whether it is going to be sunny or shiny. And then we have this other piece of information, this let's call it Y. And, this is the information about clouds, right? Are there clouds outside or not? And at least intuitively, we want to say, well, we got a little bit of learning the value of Y, or knowing the answer to the question, looking outside the window and seeing clouds has given us some information about X. And indeed, Shannon took this intuition and, among many other things, put it into a formal definition. So Shannon's notion of information, and I'm not going to give the mathematical definition, though it's not very hard, but it's just a sort of tangent to the topic of today. So Shannon's information says the amount of information that Y gives on X is a measure of the reduction in uncertainty. I just want to move this up for a second, sorry. The reduction in the uncertainty about X once we know the value of Y. So to take a very extreme case, suppose before X was X before we saw Y was let's say 50% one thing, 50% the other, and then X after Y became, after seeing Y became completely determined, so we know for sure that it's this thing and zero this, then Shannon's definition, which has actually formulas behind it, would actually give an amount of information. In this particular case, the amount of information that X gets from Y would equal 1 bit of information. And those who took a course or read things about information theory will recognize this is the reduction in entropy. We had a perfectly uniform distribution it was a 50% chance for being sunny or rainy. But after we got this piece of information, our uncertainty has been completely, eliminated. We have no uncertainty. We're completely sure that now it's going to be, let's say, a rainy day. And so the amount of uncertainty has gone down from, in this case, full uncertainty between two outcomes to no uncertainty. And we sort of gained one bit of information. So to summarize this, Shannon gave a beautiful definition. And I want to stress that the beauty of this definition is that it applies to any situation in which you have basically two variables. So X doesn't have to be sun versus rain. It could be, your belief about the stock market, and where it ends up tomorrow. And then Y could be some news about the amount of corona, new patients. Okay, so before you know that, you may have one distribution where you think it would end, and after you learn that maybe or not, you'll have a different belief. And for any two variables, you can construct this. For any two distributions, you can construct this information. And another nice thing is that this definition actually, so there's a formal mathematical definition that comes from probability and statistics. And this formal mathematical definition actually also captures very nicely a lot of intuition and is extremely useful. It's a very simple mathematical definition, but it's one that's very powerful and shows up in a wide variety of places. And a lot of statistics is about uses the notions of information. There's another one even more fundamental, which is called entropy, and it measures uncertainty in distributions, how weird and uncertain they are. And information is another measure that measures the reduction in uncertainty. So this is information, and I want to make two observations about this beautiful and very important definition of information. The first one, which will also show up when we discuss zero knowledge, is that there is some interactive or time-dependent process going on here. Meaning, when we define information, we are talking basically about the difference between two cases. The first is when we, let's say, woke up in the morning and all we know is X. And then the second one is after something happened. And this something is that we learned Y. We read the newspapers. We saw what is the corona situation. We took a peek outside the window. So there's some time involvement. There's time dependence here in the definition of information. So that's one aspect that will also show up when we discuss knowledge and zero knowledge. And the second one that we'll actually need to throw out the window or need to sort of modify it when we think about knowledge, there is no notion, or this definition has no notion or no recognition of computational complexity. Okay, what do I mean by that? It could be that, for instance, that there is, if X is the price of the stock market at the end of tomorrow, and Y is the number of corona patients worldwide and its change. It could be that there is a very, very elaborate and difficult to compute connection between Y and X. Maybe there's a way to knowing Y, learn or gain a lot of information about X. Well, in the definition of Shannon's information, this doesn't matter. Even if the distribution X and Y are extremely complicated, and even if learning, measuring the reduction in uncertainty is immensely complicated from the point of view of computers, Shannon's information doesn't care about that. And this is something that we're going to have to modify in the context of knowledge and zero knowledge, because it's all about computation, and we'll get to that soon. So Summarizing, starting from the 1940s and ongoing strong till today, a lot of data science and statistics and information is based on this beautiful concept of information, which measures some reduction in knowledge, some reduction in uncertainty. And it is a definition that is interactive and time dependent, but doesn't recognize or doesn't take into account the complexity of doing stuff. So now I want to go back and ask if there are questions about this part, because now I want to talk about knowledge. Let me go back and ask if there are questions. Just 1 second, so I'm going to answer. It might be irrelevant here, but is there ever a situation in which knowing why would give you less information about X? So that's a terrific question, and the answer to that is no. But we haven't given the definition of information. So one nice thing about information is that information is never negative. And the reason from a philosophical or mathematical point of view why it should make sense, basically, if I have a certain uncertainty that I'm starting with, that's X. And again, because we are assuming a perfectly rational, computationally unbounded creature that is doing this, to which this information refers. So that creature, if Y teaches me nothing about the uncertainty in X, or maybe even might mislead me to do it, so that perfect rational creature would simply disregard Y, in which case you would say that there was no change in the uncertainty, and then it will be at least, so information is always positive. Another question. Okay, so the second question is, if the probability of rain after Y was 0.0 instead of 1, would the information still be 1 bit? So that's another terrific question. And if you're curious, I strongly urge you to read about. So the answer to that, no, the information would not be 1. It would be something else. I'm sure that some of the participants probably can compute it and type it up. It would be, there's a formula for measuring entropy in information, and it would be something between 0 and 1. And the exact number, it's a very, in the case that we gave in the example, the computation is actually pretty simple. I mean, you need logarithms and so on and so forth, but so I strongly urge you to read about it, and it's a very important definition that is used all over the place. So the answer to that is that the amount of information would be somewhere between 0 and 1, and the exact number is easily computed, but I'm not going to do it online. If you look up Shannon information, it will give you the formula and examples. Okay, so now I want to go back and let's talk about the next topic, which is knowledge. That's actually the thing that we came here to discuss, not information or Shannon information. So let me just go back and enlarge that thing. And let me go back, and I will move the screen a little bit upwards. Let me move to a different color. So now let's talk about knowledge and zero knowledge. What do we mean? So again, we have in the back of our minds that there is notions such as information, and information actually gives you a formula with certain quantities, and you could think that maybe knowledge is something a little bit like that. But informally, the situation we have, first of all, I wanna take this aspect from the definition of information. So in the context of knowledge, we will also it only makes sense, this definition, if we think about some process that is time dependent. And the process that we have, and even involves randomness in it. So it's similar to information in that sense. So what is the process we care about? In the previous case of information, there was some knowledge about the world, or some uncertainty about the world. Then time passed, we got some information, or we got some new distribution, and we sort of deduced things about the earlier case. In the case of knowledge and zero knowledge, we are in the setting of an interaction between a prover and a verifier. And it is a time that it's interactive. So as time passes by, there's in between them, there's some channel that they communicate through, and messages are passing back and forth and back and forth. And in our case, the prover is also sending over certain, bigger pieces of information, and then the verifier is reading certain bits from them. So there's this, on one side, we have the verifier, sitting in one corner. On the other side, we have the prover, and in the middle, we have some channel through which they are communicating and sending messages. Think of this as bits. And a lot of our focus is going to be on what happens in the channel. So when we talk about knowledge and zero knowledge, we start with some asymmetry. The prover is the one that presumably knows something. The verifier is the one that presumably doesn't have that knowledge. We haven't defined yet what knowledge is. And when we talk about knowledge and zero knowledge, the prover wants to convince the verifier of something without leaking knowledge. And again, we haven't defined what knowledge exactly means. So we start with some statement, and let's make it very concrete. Suppose the prover wants to convince the verifier of something like, I know of 1,000 transactions, maybe shielded, all of them, right? We're in the context of zero knowledge, meaning, I don't want to tell you what went on in them. All are good and based on processing them, the state of some system should be some new state, whatever, A. So this is a typical generic, it's an example of a statement that the prover would like to make to the verifier. So for instance, in the case of a Zcash shielded ZK transaction, the statement would be about a single shielded transaction, something that is encrypted or committed to some shielded or sealed envelope about which the prover wants to argue something, or in the context of Starkware's scalability engine, this could be some statement about processing a large batch of transactions. So informally, we see here already that the prover is using knowledge, or the verb version of it. And the prover is assumed to have this knowledge. So the prover has knowledge of these 1,000 transactions, and based on them, the state of the system should move to A. So as a first attempt, you would say, okay, so you know what? Let's assume that the verifier is like this person waking up in the morning and seeing in her mailbox this new statement. Okay, so now we might try to sort of take the concepts of information theory and try to place them on them, and I want to argue that they won't quite fit, because seeing this statement, right, the verifier sees this statement that says, well, there exist 1,000 transactions that they're all good, and if they're all good, the state should move to A. Basically, she has all the information she needs in order to just go out and exhaustively see if it's correct. So she can basically try to look at all string bits that would encode 1,000 transactions. She could try and process each one of them, see if they're all good, according to some computational definition of what a good transaction is. Some signatures are okay, whatever. It's it's formatted according to the correct format of a transaction, and so on and so forth. And she could see what state the system should be after processing these transactions, right? She could do all of this on her own. She has no uncertainty. There's nothing that she doesn't, from an information or from a statistical point of view, there's nothing here that she doesn't know, okay? The only thing she doesn't know, you could argue, is the following. Out of all possible strings that could have led to the state A, which is the particular string that the prover refers to? But even that is not that interesting, right? Because from the verifier's point of view, it doesn't really matter which one of these strings is the one that the prover knows, right? Any one of them could be sufficient to move into the state A. So even when we start our discussion, we already see that something is amiss here. There's really, the statement says it all, and there's no uncertainty, and it doesn't seem to match up with this reduction in uncertainty. However, at a very informal sense, we could definitely see that at least certain interactions between the prover and the verifier would probably be not good for the prover. Because, for instance, if what the prover is doing is sending along this channel all the secret keys and all the private keys and all the information about the shielded transactions to the verifier, that would definitely be unfortunate, whatever the definition is. And because we're assuming that there are some secrets there. So that's another problem. So we have this vague notion of knowledge that the prover has, all of these secret keys or the particulars of the transactions that took place, but they don't quite match up with the notion of information. And we are also not yet taking into account any notion of complexity. The verifier, seeing the statement, could just exhaustively enumerate over all transactions and all strings and check which ones are good. So it seems that we are really missing some computational definition. And here came famously the three inventors of the concept of zero knowledge. So let us give them credit where. So in a paper that was published in 1985, but circulated for a long time before that, for a couple of years, and was rejected famously from some, prominent venues because a variety of reasons. So Shafi Goldwasser, Silvio Micali, and Charlie Rakoff came up with this beautiful definition of what knowledge means. So, and they're going to retain this notion of interaction, but they are also, and randomness, but they are also going to pay a lot of attention to computational complexity. Like how much time it takes. And they said something like this. Well, there's the verifier here, there's the prover here, and there's the channel that is through which which we view things. And messages are going back and forth and back and forth. So informally, we say the interaction, right? This proof, this interactive proof is zero knowledge or leaks zero knowledge if anything V could gain from seeing what goes on in the channel, she could generate efficiently without seeing the channel. And it takes a little bit of time to sort of see the why, both the beauty and the power of this definition. But informally, it says that if we could show that whatever the verifier has seen in the channel when interacting with the prover, she could have also simulated by herself without talking at all to the prover, then the prover should feel comfortable interacting with the verifier and doing this whole process. So again, think of it from the point of view of the prover. The prover has some secrets, like in this red part above. The prover knows a bunch of transactions, and there are a lot of secrets there, and so on and so forth. And the prover would like to interact with the verifier and pass bits along. But the prover is worried that something will leak about passwords or private details of the these transactions. So the prover is hesitant. So along come Goldwasser, Mikhail, and Rakov and say, well, here's a situation where you wouldn't mind sharing or interacting with the verifier and doing this thing. If we could show to you and prove to you that anything you suspect the verifier has gained from interacting with you, the verifier could also just generate by itself without talking to you at all. We will actually give it, a process through which it can simulate talking to you. Then you, having spoken to the verifier, interacted with it, you really revealed nothing, right? If you are the prover and you are suspicious, a new question comes along and you're asking yourself, wait a second, if I answer this question, will I be leaking information? So the GMR definition and protocols that subscribe to, that have provable zero knowledge, are such that you're promised as a prover that as long as you're following this protocol, you don't have to worry about the questions that the verifier is sending your way, because any answer that you give the verifier, you know that the verifier could have generated by herself without you. So again, the similarity to the notion of information is that we, in this case as well, have interaction and time dependence, because we are talking about a certain view, which is this channel through which we are looking and measuring things. We are looking at basically at the strings that pass along here and the objects that are sent from one side to the other. But in stark comparison to the previous case, it's all about computational complexity. How easy or hard is it to generate the messages that are passing on in this channel? And it is much less about statistics and distribution. The whole point of zero knowledge is that you can promise the prover that the verifier could have generated what transpired in the channel without interacting with you. I'll give a very stupid example, and then I'll go back and answer some questions. So suppose I would like to prove to you that I can somehow control the laws of mechanics or physics, and I can make it so that every time you toss a coin, you pick the coin and you toss it, in your room, I will make it fall on heads. Okay, suppose I wanted to, and I don't want you to to know anything beyond that. So now we could run this experiment where I tell you, okay, please toss a coin. Well, let me sort of concentrate, work my magic. I'm telling you, please toss your coin. You toss the coin. You see it came out heads. I say, let's do it again. Concentrate again. Toss your coin. Again, it's hit. We do it, whatever, 10 or 20 times. Now, the point is that you, as the verifier in this case, could have done the same process by yourself. Sorry, you could have simulated. You know what the outcome would have been without interacting with me or without getting, my influence on it. You know in advance that if I'm speaking the truth, what you would have seen is a sequence of heads. So this sort of mock example, the fact that you actually saw this particular transcript where it all came out heads, I could sort of rest assured that just from the fact that you saw this, you have not learned how I work my magic, because you would have known, like if I'm speaking the truth, you would have known that this is what would have happened. So I'm going to pause here and ask if there are questions about the notion of zero-knowledge proof. Okay, so let me go back and give a slightly more, so these talks in general are, as I said many times, these talks are not intended to be formal at all. So I'm going to give an informal definition of what is a zero-knowledge proof. And again, you can read up in a whole bunch of places. So we say, let fix some interactive protocol for proving statements involving, and this protocol, the protocol involves a prover and a verifier. We always assume, we must assume, or the verifier is an efficient, so computationally bounded computer. Meaning, we assume that the verifier can't, exhaustively search over all strings and see, try each one of them, and it can't, compute the lookup table of, it can't sort of, enumerate over all inputs to SHA-256 and things like that. Okay, some notion of limitation on the verifier side. Okay, we say this protocol achieves zero knowledge if there exists another machine another efficient algorithm called the simulator. So usually we, P is for prover, V is for verifier, and S is for simulator. Such that for any statement, X, the view seen on channel between the prover, between the verifier and the prover, is equivalent to the view generated by the simulator that sort of operates with the verifier. So the simulator can get the code of the verifier and produce some view. So let's give a little bit of explanation what we mean by this. Wait just 1 second. So again, let's suppose that the statement that we start with is a, let's go back up here and see. So there's this red statement, right? This is the statement we care about. The prover claims knowledge of 1,000 transactions. They're all good and so on. So now the protocol, now we're going down here. So now there's this protocol where you must understand or assume that all of these protocols, they involve randomness and interaction, which means that the verifier is tossing some coins. It tosses some coins. This is a coin, and it tosses a bunch of coins, and then it spits something out, and goes here. And then the prover groks this and spits something back, also using randomness. And then the verifier tosses some more coins, and so on and so forth. And at the end of the day, we have this transcript of the channel. It's a sequence of messages. Okay. Now this is just one, one of the possible transcripts that could appear on this channel. Because if we sort of start from the beginning with the same X, the same statement, and the verifier tosses coins again, it will maybe generate some other message, and the prover, based on that and its own coin tosses, will answer with some other message, and then so on and so forth. And for every choice of coin tosses that the verifier does and the prover does, there is some transcript. So actually what we get is that the transcripts form a certain distribution, right? There is some probability that a particular sequence of messages will appear. Maybe it's the uniform distribution. Maybe all messages appear. Maybe only half of them. Maybe one message appears quite often and others don't. But there's some distribution. Okay, there's the distribution on all. So this is the distribution on, this is like probability, and this is probability, and this is, the space of messages or transcripts. Sorry, let's make it transcripts. So there's some histogram transcripts. There's some histogram. Certain transcripts appear more often than other, and there's a certain distribution on transcripts. Okay, well, protocol is zero knowledge if, when we define this protocol, we can also define some S. If you allow it to use V, it will spit out. It's a random process that spits out a probability, and this probability will be exactly the same. So we say that, let's call this, this is 1, and this is 2. So if 1 is equivalent to 2, if the two distributions are the same, and S is efficient, meaning it can sort of sample and generate. You give it randomness, it spits out a transcript, and it does so efficiently. If the two distributions are the same, then you say that the proof system has zero knowledge. And the rationale here is that, again, the prover should not worry about interacting with the verifier, because any particular transcript that would have came out, so this is, any particular transcript that could have come out from this interaction is something that, stepping into the protocol, the prover knew that the verifier could generate efficiently. And it could generate efficiently because the protocol designer, when she designed the protocol, she already proved the existence of the simulator. Okay, so now let me go back and see if there are questions. Are there any questions? By the way, can you all hear me? Or am I speaking to myself? Hello? Ah, okay, good. So, okay, cool. So now I want to move on to the next and last topic for this particular talk, and explain how we instantiate this in the world of Starks. So how do we go about? Let me just move back to that thing. So we have this very strange definition that says if you want to create a zero-knowledge protocol, you have to come up not with two things, you have to come up with three things when you define the protocol. You have to say what the verifier does, you have to say what the prover does, and then you have to also say what the simulator does. You have to think about the simulator and basically present it along with your protocol and say, look, world, the protocol is zero knowledge because if you see what the interaction between the prover and verifier looks like, we can already promise you that we can simulate that interaction without talking to the prover. Now, the really tricky part is doing so not just for the, what is called the honest verifier, the one that you decided and you defined as the protocol definer. That's easier. It's sometimes called honest verifier, zero knowledge. If we assume that the verifier operates according to your specification, it's non-trivial, but it still is easier than the more general case. Because you have to worry about the verifier not playing along with the protocol. Maybe the verifier is supposed to be there to sort of check that the proof and the statement are correct. But maybe the verifier does not care about that. The verifier wants to extract some secret key and use it in order to steal money. The verifier wants to learn something about one of your customers. The verifier does not care about the correctness of the statement. Maybe it knows or it assumes that the prover is honest, so it doesn't care about that. So we have a harder task in zero knowledge definitions, and that is to create a simulator that for any verifier, not just the verifier that you thought about, it can simulate it. So let me also make it that for any and for any verifier, this thing happens. The view scene generated by the simulator that sort of gets the verifier as a black box or as a, as a piece of code can generate a view on the interactions that is exactly equal to the view that the verifier will actually see. Now, as usual, I want to say that first of all, grossly I'm hiding a lot of details under the rug. So for instance, there are many variants of zero knowledge. The one I'm talking about is actually known as a perfect zero knowledge, universal black box perfect zero knowledge. There are many, many other variants, but I want to give the most basic flavor. It's also the strongest flavor, and luckily, at least in Starks and IOPs, it's actually not far from the notion of zero knowledge that we obtain. Okay, so how does one go about this very difficult task of constructing zero knowledge, which means that you have to, again, you have to prove that you have to construct a simulator. So now I want to talk about how you construct simulators. First of all, in the general case for interactive oracle proofs, which are an abstraction of the model that we use when building Starks. So what is the model? We have our prover here, and we have our verifier. The verifier always sends random coins. Okay, so like random 1. Now the prover basically can send messages, but more often the prover actually sends sort of a USB stick. So USB stick. So think of some memory object that contains a lot of random access memory. So this is USB 1, then there's some randomness, R2, and now there's a second USB stick. So on and so forth. And at the very end, the verifier also makes queries. So what does it mean? The verifier reads, one piece of information from this USB, maybe 2 pieces of information from this USB, and takes into account the messages and so on and so forth. So the transcript that we have, the transcript that the IOP transcript, what does it have? It has verifier messages. These are one. It has these prover messages, and it also has, at the end of the day, when everything is open, it has the USB sticks. These are functions restricted. So this is F1, restricted to the query set that you actually made. So you didn't read all of the USB stick. You read just a few entries from it. And then there's more randomness. And then there are more, the second USB stick, there's a bunch of queries that you read. So maybe you read, maybe this query set was the first 3 bits of the USB stick. Maybe this was the second one you read from it, the 3 last bits of the USB stick. And that's the transcript. So when we build a simulator, what do we need to do? We need to show that whenever the verifier is sending randomness and the prover should send back messages, we need our simulator to basically supply the answer to the messages. But in most cases, in most protocols, the messages don't appear. What really appears are the USB sticks. So we need our simulator to be able to fill in the query questions at the time they arise in such a way that when you look at this transcript and you measure the probability that it shows up, the probability that this particular transcript shows up is exactly the same probability that the transcript would have shown up if you replace this with a prover that actually has the statement in hand. So we need to build a simulator that can answer these queries in a way that the distribution that you achieve is exactly the same distribution and exactly the same probability of seeing these answers if you would have replaced the simulator with an honest prover that knows the statement, that knows the proof. And this seems like a pretty hard task. Think about the case of, the statement could have been that red statement that we talked about, right? The statement could have been, I know of 1,000 transactions. Well, the simulator does not know of these 1,000 transactions. The simulator does not know of the secret keys of all of these transactions. So how on earth is the simulator going to guess and fill in these answers correctly? So let me see if there are questions about this, and then I'll answer this mysterious question. Okay, Pankaj is asking, who is supposed to generate the simulator? Is it the protocol designer? Is it the prover or the verifier? So the answer to that is very simple. The protocol designer who claims that he designed a zero-knowledge protocol is the one who must present the simulator and then also formally prove that certain statements about the transcript generated by the simulator. So you have to first design it. And you have to design 3 things. You have to design the prover, the verifier, and the simulator. And you have to argue formally that the distribution that the simulator produces when interacting with the verifier is equal to the distribution the verifier would have seen when interacting with the prover. Terrific question. Second question, Yaakov. In case of non-interactive ZKP, isn't an honest verifier zero knowledge sufficient? If not, then when are they sufficient? When not? So this is an advanced question that I prefer not to go into because I don't think we'll have time to talk about non-interactive ZKPs. It's a different model, but let's take it offline. Question, Skyheart. After Shannon and Colley, who discovered extractors? Can you introduce extractors in your schema? So I wonder if you're asking about knowledge extractors or randomness extractors. These are two very different creatures. Knowledge extractors were defined, I forgot who were the first to talk about proofs of knowledge. I know that the standard definitions come from a paper by, I think, Belare and Goldreich, definitely Goldreich. Okay, knowledge extractors. I'm going to have to take it offline who was the first to define them, but time permitting, I will also discuss what do we mean by knowledge extractors, because so far I've only spoken about zero knowledge in simulators, and knowledge extractors are another topic that maybe we'll have time to talk about. Okay, so we'll see if, so to your question, I'll see if we have time to discuss extractors in the schema, okay? But for now, let's just focus on simulators. Good. Okay, so how do we go about and do this? So I want to explain how informally you can take an IOP transcript or an IOP protocol, and in particular something that underlies a Stark, and make it zero knowledge, okay? And for that, we have to very briefly, recall what the Stark, what does a Stark proof? What do the oracles consist of? So, what the prover, what the prover really sends first is some table. This is supposed to be some function f1 that goes from a certain set to a finite field, and it's supposed to be the degree of the function is supposed to be less than let's say the size of the evaluation domain divided by 8. So it's some low degree polynomial. The verifier asks something about it. There's some, and then there are a bunch of other. This polynomial should encode the transcript. Sorry, encodes a computation. So this polynomial, really what happens is it talks about maybe here, in the first part you have the secret key, it appears here, there's secret key 1, and then there's secret key 2, and there's a whole bunch of other information, and then there's some, some computation going on. And then you take all of this information and you basically compute a low-degree extension of it. So you apply a Reed-Solomon encoding, and you interpolate the polynomial among all of these points, and then you evaluate it on a whole bunch of other points. So that's one thing that you do. And then we know that the verifier at some point is going to ask certain queries. It's going to ask, what's going on here? And it's going to ask, what's going on here? And it's going to apply some polynomial constraint C to the answers. Maybe it's going to read, if this is the first answer and this is the second answer, maybe it's going to check whether, it's going to check whether 5 times x1 squared equals, 6 times x2 cubed plus 3 times x1 times x2. Now, maybe this is the kind of constraints that it checks. And if it sees that this constraint passes, then it's going to be happy. Otherwise, it's going to be unhappy and reject. So basically, the way our systems work is that we expect the prover to send a bunch of polynomials. The verifier is going to make some queries into these polynomials and plug them in to some other low-degree polynomial like this constraint and check whether that constraint equals 0 or whether the two sides equal one, one equals the other. So our main concern here in terms of knowledge leaking out is that the first concern is that the malicious verifier will simply go here and, it will sort of go here and make a query and ask for the value of the function at this very entry. And now the answer to this is actually the first secret key, which is, of course, really bad. So one thing we want to make sure of is that the verifier never, we want to make sure that the verifier never queries things like the secret key. This is not yet a proof that, secret key 2 and so on and so forth. We definitely want to ensure that this never happens. So the way this is addressed is, so the solution to getting this done is have prover evaluate the function f1 over some domain S prime that has 0 intersection with S. Okay, so if this was the evaluation domain, right, we will actually make the prover send to us f1 only over this area, only over this area S prime. So this area S prime is not going to include any part of the transcript in any one of the secret keys. So it's already, this is already giving some protection to the prover. It's at least not making it easy for the verifier to learn the secret keys. But of course, that is not enough. And the reason, or another way to see that that is not enough, has to do with linear algebra. So let's look at the answer x1. What is x1? x1 is the evaluation of a polynomial f1. And what's f1? f1 is the interpolation of a whole bunch of secret keys and some extra change. But interpolation, so moving from these values to the coefficients, is actually a linear transformation. So it's a very efficient, there's a matrix that would, given these values, given the secret keys and everything, would output the coefficients of the polynomial. And likewise, putting down the evaluation, no matter on which evaluation domain, on S prime, is also given by some other linear operation. There's another matrix. So basically, there's a linear transformation that, given all of these secrets, will output each and every one of these entries. So in particular, whenever the verifier queries any query in the domain S prime, it gets information that is some linear combination of all of the secrets. So the verifier has learned something. It learned one linear combination. In fact, if the verifier were to make as many queries as the degree of the polynomial f1, then by linear algebra, the verifier would have learned enough information to completely reconstruct all of the secrets. And again, that's really bad. So we thought that we made progress, but we really made no progress. We made very little progress, because the verifier, with each and every query, it is already learning something. It is learning a linear combination of the secrets. And the way to circumvent that is to add a little bit of salt, which is a common thing. So what we do is we allow prover to use f1, not of degree, 2 times the size of S. Sorry, here it should have been, well, I mean, the degree of the polynomial here is the size of the evaluation domain, which is the size of S. And then well, I mean, the size of S prime, you take it to be, let's say, A times the size of S. And then the degree of the polynomial F1 is actually exactly equal to the size of S. So what we do is we allow some slackness. We allow the prover to use, to give us any F1 that has twice the degree that it would have needed in order to encode the information. And now what the prover does, and this is the sort of final trick that I'll talk about in this context, is it takes S, it puts here the secret keys and all of the information, and here it puts randomness, just fills it with random coin tosses. And then it takes, so this is maybe S tilde, and then it takes this, so this is of size, this is of size D, this is of size D as well. It's allowed degree 2D. It interpolates this higher degree polynomial and then evaluates it on S prime. And that's actually what it provides to the, what it sends to the verifier is this thing evaluated on S prime. It is of twice the degree, and half of the entries that were used in order to create this evaluation table are completely random. And what happens is that it turns out that as long as the verifier makes less than D queries into this new function, it actually, what it sees is a completely uniform distribution on random elements. So in other words, what happens is that, I don't know if you hear, but my young son is being put to bed, so he's offering some, he's unhappy for going to sleep. So, but I apologize for that. In any case, the prover in this situation, by adding salt, creates a new code word that is still of low degree. It is twice the degree of the previous case that had no zero knowledge. So you lost a little bit in the degree. But in exchange for that, you are offering the verifier a USB stick such that you know in advance that when the verifier reads less than D queries, you know what the verifier will see. The verifier will see uniformly distributed bits, period. So to answer our question, how do we construct a zero-knowledge simulator in the case of things like Starks? A large part of it has to do with this addition of salt. And this, we allow the prover slackness, increasing the degree. In exchange for increasing the degree, we know in advance that the verifier will see on all its queries in this phase uniform field elements that are independent of any secrets or any information that was used. And because of that, we actually can construct a zero-knowledge simulator efficiently that, given any verifier, no matter what queries it makes, as long as the number of queries is small enough, we can fill in the answers and create this transcript that is needed for proving zero knowledge. So I'll go back and answer some questions. So is the choice of 2x the degree arbitrary, or is smaller degree insecure? That's a terrific question. And the answer is no. The choice of 2x is just for didactic reasons here. You need degree slackness that is as large as the number of queries the verifier will make. So if that number of queries is 5, you need to allow a degree slackness of 5. If that number is 500, you need a degree slackness of 500. That's the correct answer. Maybe +1. Okay, terrific question, Patrick. Okay, next question. Skyhard asked, after Shannon and Mikali, who discovered knowledge extractors? Can you introduce extractors in your schema? So if there are, I can now, I can now explain what knowledge extractors are. And I'll go back and, we'll do sort of an encore. We'll explain what knowledge extractors are and actually how we get them in the case of our IOPs. So what do we mean by a knowledge extractor? Often we care, what we really want to know is not just, here, let me just change color. So someone can come and say there exists a some information in a sealed envelope that can be used to pay someone. That's one statement. There's another statement which is slightly different. And it says, I know of, and now it goes back here, the information in a sealed envelope. Now, we would like to design systems in which if someone comes and says, well, I can argue that there is information in that sealed envelope, or I can argue that there is a password that would allow this user to enter the system. There is a password that will allow this administrator of Twitter account to send these bogus messages on an account, on account of Joe Biden and Elon Musk and all those. Well, we don't want to allow that person to enter the system, but we are willing to allow the person that says, I know the particular password of a system administrator of Twitter, so please let me in. Okay. So the question is, how do we formalize the difference between the two? Between there exists X and I know X. That's the difference we want to distinguish between. So in comes this notion of a knowledge extractor. And the notion of a proof of knowledge. So a proof of knowledge is a protocol that, once again, you as protocol designer can show it is a proof of knowledge. And how do you show it as a proof of knowledge? Just like we, if you wanted to show that it is a zero knowledge proof, you had to build an efficient simulator. In this case, you need to build a knowledge extractor. What is a knowledge extractor? A knowledge extractor is yet another efficient algorithm. And this time, so here we have our prover. Here we have our verifier. Verifier always on the right. Here we have our prover. Here we have the channel. Remember that when we talked about the simulator, this is where the simulator lived. Well, the extractor actually lives here. So the extractor is something that actually encapsulates the prover. And you can think of it as some sort of interrogator of something, what it does, the extractor, it's another algorithm, but it can send messages to the prover. It can rewind it. It can sort of poke questions into it. Again, we assume that the prover is some black box functionality that sends messages and so on. And what the extractor must produce is a witness. It must produce the knowledge itself. It must produce. The extractor must, torture the prover, work with it, but do this all in efficiently in a small amount of time, and then output the the passwords and the secret information and all of the stuff that were claimed to exist. Secret keys, etc. And then all the information that was needed. Okay, so again, if you want to prove a proof of knowledge, so let's see. If you want to be, if you want to be in the business of creating protocols, in summarizing, to build a ZK proof of knowledge system, here's your checklist. Now you better bring me your prover. You better bring me your verifier. And this has to be efficient. And of course, you have to prove things like, completeness and soundness. Then for ZK, if you want to check that list, you have to bring your simulator that works with any verifier, malicious verifier. And you have to bring your extractor. And it has to work with an honest prover, but it can rewind it. We're not expecting the extractor to be able to extract information from some prover that is just messing around and doesn't know the proof. But any prover that is convincing and manages to convince the verifier of the statement being correct, your extractor should be able to work with it and extract and give us a witness. And just to go back, and if we ask ourselves, in the case of an IOP, how do you get your extractor? Well, the idea is that the extractor is going to actually take, the extractor gets this, right? Sorry. The extractor gets this, and it basically reads all of it. And from it, with an amount of work, you need to show that if you allow the extractor to read all of this information, it first of all has enough information to decode and go back and find the secret keys. And moreover, you can show that any prover that manages to successfully convince the verifier that the statement is correct, necessarily the extractor will be able to extract from it, the witnesses and secret keys and everything. So let me go back and see if there are questions. Okay. Adrian is asking, there is some leniency for S prime's extension that if there was some corruption to the USB string, it will still verify, or does it have to be exact? Verifier returns 0 for all strings, 1 for the exact S prime. Terrific question. So this goes to, the way to answer this is to talk about completeness and soundness. Completeness and soundness are what address this question of, the leniency. So we are in a model where we assume that there is no noise and no mistakes. The only kind of errors in information would only come from a dishonest, malicious prover. So the systems that we build and all IPs and IOPs and PCPs and these other creatures that I'm aware of, all of the systems that are built this way have typically perfect completeness, which means that we know that if the statement is correct and the prover is the one that operates according to what the protocol specifies, everything will line up perfectly. In particular, in the case I described, what the verifier will receive on the USB stick will be a polynomial of exactly an evaluation of a polynomial of a degree exactly, at most 2D, and this will be a perfectly honest evaluation. So there will be no leniency. The trickier part, and we actually had a whole Stark at Home webinar dedicated to it, is that of soundness. Along comes a malicious attacker that claims it knows a proof of some statement where it doesn't actually know. And then one of the things that prover will want to do is to submit a function that maybe using the leniency or some other angle, the function will not be a perfect evaluation, but maybe might be something that is slightly corrupted. If you would have read the whole USB, you would have seen that there are some errors there. So when you construct a zero-knowledge protocol, it first of all has to be a proof system. And the definition of proof system also has to check the soundness bullet. To check the soundness, you have to prove that no matter what shenanigans the malicious prover is trying to throw at your way, your verifier will reveal them and find that it's being cheated and will just throw that proof or prover away. So that's a different aspect that we did not discuss here, but it's preliminary. So first you have to prove that your protocol actually is a proof system, that it has completeness and it has soundness. And only then can you attend to the bells and whistles, such as showing that it has zero knowledge and then that it is a proof of knowledge. It's a great question. Okay, so I just want to summarize. And again, if you have your any residual questions, now is the time to type them. I just want to summarize what we discussed today. Let me maybe use this option of making things smaller. So sorry about this. So let me pick a different color. Now let's go with this. We talked about information, and we said that it is interactive. Already this definition, but no computation is involved in the definition. And then we talked about knowledge, and we gave the marvelous definition of GMR. And we said that it is interactive. Again, the whole definition is interactive. It involves randomness, but is all about computation and requires simulation. So in order to prove that something is zero knowledge, you need to construct an efficient simulator. Then we spoke about IOPs and making them zero knowledge, and how we do that with degree slackness. There are more things that go into it, like masking and low degree testing that we haven't. So this isn't the whole trick, but it's the essence of it. And then there's some auxiliary things that need to be done. And the final thing we spoke about was actually due to a popular demand. What's going on here? So we also talked about knowledge extraction. And I just want to say there was no Waldo and there was no cave. I think that's a first. So I'll go back and ask if there are any questions. Okay, so I see there are no more questions. So I want to thank everyone again, and hope to see you next time in roughly 2 weeks. Thanks a lot. Bye.